So without further ado, I'd like to introduce Fergus Kidd, and he's part of Avanad's Center of Excellence for Emerging Technologies.
Hi, it's great to be here. Thanks, Alicia. Yeah, great introduction. I certainly have a lot of toys and tools under my desk to play with. So thanks so much for inviting me. And I'm really pleased to be able to speak to you about thinking machines today. So I'll go ahead and start off the presentation. Just to give a little bit of an introduction to me. So as Alicia said, I work at Avanad's emerging technology team. What we essentially do is applied research and development in areas of interest for us and our clients. There's a few examples of that on the screen here. So we have robotics, which I'm going to talk a little bit about today, 5G, quantum computing, VR and XR, which I actually spoke at a global AI event last year about, which is really amazing. So it's great to be invited back as well. So thank you for that. Just going to check my screen. Excuse me. So yeah, absolutely great to be back presenting to you today on thinking machines. Also really glad to be following Veronica, because a lot of what I'm going to talk about today actually has some crossover with what we've already been hearing about, which is really, really great. So what I want to go over today for you is an introduction to Azure Digital Twins, which we'll talk about more in detail, and also an introduction to thinking machines. As part of the explanation and the process that we went through, I'll introduce you to Project Malmo from Microsoft, as well as Azure Digital Twins, which is also from Microsoft as part of the Azure stack. Two really cool pieces of technology, and show you a bit of what we've been doing in action. So first, I wanted to just quickly go over what is a digital twin. So a digital twin is a virtual replica of a physical entity. That's what it traditionally is. That's what the Azure Digital Twins offering has been built around. So that usually includes a data model representing the data within the system. So if this is a physical system, like a series of sensors, for example, or for example, a smart building, which I'll talk about a little bit later, the data model may be representing data that's coming in and out of lots of different IoT sensors. It also includes the analytics or algorithms to process and manipulate the data. So that's kind of a layer on top. This is a whole field of potential for machine learning and artificial intelligence of itself. So you may see Azure Digital Twins around, and they may be something that you can get involved with as well in other contexts than just thinking machines. And often they also have controls. So this is the idea of actually feeding back into the systems, using the data, using the analytics to make decisions about the system. Traditionally, these are for physical systems that closely aligned with the physical and digital world. They help collaboration between different stakeholders. So if you have, I'll use the idea of a smart building again, you may have different people using a smart space in different ways. You may have users, administrators of that space. You may have facility managers of that space who are interested in things like electricity consumption, whereas the users may be more interested in, hey, what space can I use right now? And they really help to integrate and abstract the underlying systems. I'm not going to be talking about Azure Digital Twins really representing a physical system, but we are using them to represent a data model and a system, a kind of digital system, which is quite an interesting use case, I think, but it may not be a use case that's typical of Azure Digital Twins in general. So what do we mean by thinking machines? Well, we kind of summarized it in our team like this, that thinking machines are part of the journey to an artificial general intelligence. So we're some way off that, but these can be realized today where systems are assigned a task, maybe they self-identify the task and how to solve it, work on that task, come up with a conclusion or an output, and that can be supported and supervised by a human at the same time, which is a really interesting and cool idea to have kind of that human in the loop as part of that system. So I want to kind of explain thinking machines a little bit better, which is why I have this robot behind me. I also have a video on the screen, which I'll play for you, of the robot kind of like moving around in action. So this is a stretch robot from the Hello Robot company. This is designed as a kind of cheap and open source robotic platform that's going to be really good for developers that are exploring robotics in different ways. So we have a camera system, an open source camera system. We have some different servos, some lifts. We can move this base around, this robot, move it around the room. We can grip objects, and we can use the camera to do that. So what does the stretch robot have, and how does this apply to thinking machines? It's got lots of well understood components. So we have a camera system, it's open source, we understand that well. We understand how that works. It has an open source library, open source drivers. The motors all use a open source system called ROS Robotics to actually drive the components. We understand that. We get lots of data from the camera. All of the positioning sensors on the robot actually feed us back data all the time. And we have also, you can just see in the image here, you can't see behind me, but if you can see my pointer, I'll just make it into a laser. See here at the bottom, we actually have a LiDAR system which can map out the space around the robot in order that we don't collide with objects. But what's missing from the Hello Robot is some intelligence, some sense of communication, and the kind of what we call the orchestration of abilities. And that all leads to like adaptability. So at the moment, with all these open source components, what we can do is write code for very specific tasks. We can write code, for example, to pick up a glass from a table by recognizing the glass with a camera. Another interesting thing which links very heavily into what Veronica was talking about earlier is we actually have a chatbot running on, or a bot running on this robot that we call Rory. So we have a Lewis, so you can actually give instructions to the robot using the speech to text services. It will announce what it's doing using the speech to text, and it will move around based on voice commands. Using that, it also has a Q&A maker in it. So if you ask it questions, it will be able to actually, give you some basic responses. We've also included the default bot personalities that are available with Q&A maker, so it will answer them in kind of a way as if it has kind of a personality associated with it as well, which is really cool. We use the text to speech as well, which Veronica was talking about, with a British voice. Obviously, I'm based out of London, so and it's currently in my possession, so I gave it a nice British accent, which is kind of fun. But as Veronica said, there's a whole host of different languages, genders, different voices that we can use. So this is kind of gives you an idea of what I'm going to start talking about, is that we have this system which we can represent physically, the parts move, but we can also represent that digitally as part of an Azure Digital Twin. And what we have is lots of disconnected systems. So we have the camera, we have the motors, and they're not necessarily working together unless we do something, and they're definitely not working together in an intelligent way. Quite often, these platforms are running scripts which use individual pieces of AI. For example, we use the cognitive services for face detection and object detection, so it can actually tell you what it can see or who it can see, but it's not really using that in an intelligent way. It's not using that information in an intelligent way, although we can get that information out. So the idea of thinking machines is really taking all of those separated pieces and trying to orchestrate those individual pieces of AI, or those individual pieces of machine learning, or what might be quite simple sensor readings together in a way that we can actually understand the environment. And the goal is to actually tackle a problem that we haven't seen before by using our the robot or the system's learned experience from other attempts. So quite a complicated challenge, and I'm going to talk as best I can about pieces of that. So what do we need to do in the first instance to make Rory more intelligent? We think of this when we talk about thinking machines in terms of agents. So for example, the object detection from the camera, which might be a Microsoft Cognitive Service, in our case it is an example of an agent. An agent is a piece of artificial intelligence, a piece of simple code, or a piece of machine learning that can achieve one specific goal. It can create a data product, or it can do something. In some cases, they can be more intelligent, as we'll see in next examples. So what we're looking for is cases of multiple agents working together. So maybe the camera system uses multiple cognitive services together to inform its movements. So maybe it might drive to a person it recognizes if that's the command you give it, or it may pick up a cup from a table by recognizing what the cup is that the robot needs to look for the cup, find it, and then grasp onto it, make contact. Quite complicated challenges that we have the ability to do at sort of an individual component level, but we need to stitch together. Also learning from experience, so learning from when we go wrong, learning from when we get it right, and a human input where necessary. And often that's for that training purpose. So we're actually, a human is saying, hey, you did a good job on this, you did a bad job on this. Obviously, it's not always possible to use a robotic platform like I'm lucky enough to have access to. So I want to introduce to you another piece of technology which is really interesting, and I'll give you a few demos of this as well. This is a project out of Microsoft Research that's called Project Malmo. You can visit the GitHub there, or just Google Project Malmo, and it will take you to some pages where you can learn about that. And this gives a really nice visual example of like what I'm talking about when I'm talking about agents and how agents are working together. In this case, the player is an agent, so that can be a human player agent, or it can be a computerized player agent, and I'll take you through a couple of different scenarios. This example, they've actually got two players playing a game together, but I'll go through it in a little bit more detail. So what I want to try and do is move on to a live demo, so please forgive me if this all goes horribly wrong. So just to introduce you to Project Malmo. So what I'm doing here, and it's going to break on me, isn't it? Or every time. Okay, I may have to default to my videos. That's quite annoying. But Project Malmo runs in a number of different code languages. Let me just try and, whilst I'm talking about it, just restart everything. Let's see if we can get this. The Project Malmo is available in a number of different languages. I use it in Python. And what it basically allows you to do is to access the basic functionality within Microsoft through Python, so which is really cool. So we can have a look at different aspects of the Python. We can move the player around. We can use a bunch of senses, so we can sense when there's certain blocks or objects within the game. And in thinking machines research and kind of a lot of multi-agent machine learning and artificial intelligence research in general, gaming platforms are actually used quite a lot because they have quite complicated tasks that we're usually expecting humans to partake in. That may be like fighting aliens, or building structures like in Minecraft, or completing some task. Minecraft's a great platform because it's so flexible. We can assign whatever rules and tasks we want to it, which is a really great thing to be able to do when we're talking about agents. We can run machine learning in it. Agents can learn, which is all really useful. So hopefully now I'm going to show you an example of how we can actually automatically generate a world within Malmo here. So we've generated a 3D block structure. In this world, I have limited control. As a human, I could walk the character around. But as we can see in this example, nothing is actually happening. So it's not very interesting. All we've done is generate a world. So if we go back to the code, what we can actually do is send very simple commands using the code input. So we can send commands to jump, we can send commands to move forward, which is what we're going to try and do in this world. So I will cheat and go to the solved version of this particular tutorial. And for whatever reason, we're not working anyway. So the idea is that we can use simple Python commands to actually control the agent, but then we can also do more complicated things with an individual agent. So in this example, and I'll use the video instead of trying to demo this time, unfortunately that wasn't working. In this example, what we're doing is we've created a small maze for an agent. We've given it no knowledge of what's actually going on in the world. We've also removed its ability to sense what's around it. So this agent can't actually detect the lava without falling into it. And what we're doing here is we are using Q-learning to actually help the agent learn where that lava is. So every time it makes a mistake and falls into the lava, it gets a low score. Every time it's making a successful path, it's actually getting a good score. So I'll play that again. And what we find is the agent will slowly move around the map, making mistakes, but then learning from those and actually learning to survive and find the exit. Obviously, if we then change the map or the maze, we're going to have different results because the agent isn't actually going to be able to find its way out, and it will have to relearn that. So an interesting kind of example of a single agent problem. What we can also do with Malmo, which is really interesting, is we can actually have multiple agents. So in this case, we have two instances of the Malmo running the Minecraft. So we have two different agents talking to each other. And this time they have a common goal. And the common goal is essentially for the player at the top of the screen to rescue the player at the bottom of the screen. Unfortunately, this video gets a little bit dark because it takes quite a long time and the Minecraft world goes to light. But essentially what is happening is that the two agents are learning to communicate, or in this case, they're programmed to communicate, but you can imagine that they learn that behavior, and they are actually communicating. So the one at the bottom here who's standing on top of a pillar is communicating instructions for his companion to actually build the structure that's required to release him from the tower safely. So you can imagine you can use this platform to actually grow multi-agent problems quite quickly. And the great thing about Malmo is that you can make up any scenario or game that's possible in Minecraft. So you have lots of different block types, you have lots of different items that can all be used. You have large worlds that the agents can explore. They can work together to build structures. They can work together to achieve common goals. So really, really super cool platform. And you don't necessarily have to have a robotics system to use these agents and start programming and using some machine learning or artificial intelligence. So how does Azure Digital Twins come into all of this? I'll give you another demo which will hopefully work this time and kind of explain that. So it's really important to, especially if I just go back and show you this mapping example again, actually. We kind of talked about how the system learns to solve a particular problem by trial and error, essentially at the beginning. It gets a score for every time it makes a successful attempt. So the agents can learn individually to do quite simple tasks, but the agents themselves are only doing small pieces of work. So it's quite important that we have some memory of what occurred in these events. So if a similar task comes along, in this case, it would be the same maze or a very similar maze, we can actually use and utilize our learning from a previous attempt to continue. Now, when that's quite simple when you have a single agent problem, because you just use the information that we're building up here, right? We've essentially just built a map of the current maze. But in more complicated scenarios, we may be trying to learn from, or we may be trying to give a score to a method rather than a particular pathway. So, in general, in these types of mazes, going forward and to the left seems to work a lot more. So we give a score to that method rather than the exact path. So it becomes important to save information about how we actually ran these different pieces of artificial intelligence. It becomes important to retain some information of what happened in the run, the sort of data output we might get, because in more complicated situations, the agents might actually be producing some quite complicated output. So it may be a piece of computer vision, like an image goes in and some text comes out, and then the next agent takes some text in, does some analytics on that text, or some natural language processing, and comes up with a conclusion based on what's important on that image, or whatever it might be. So it's quite important to save those and have some understanding of how those events and those, what we call memories, essentially link together in the history. And what we decided or found is that a really good way to do that is a graph data structure, where you can have some quite fixed elements. So those elements may represent the agents, they may represent the data that went into the agents, they may represent the data that comes out of the agents, they may represent some additional information about what the agent did in a particular scenario, and then we can later analyze how they work well. The benefit of using a graph structure is that we can then link those pieces of information together. So we can directly link agents to input data and output data. We can directly link agents to results, and all sorts of interesting setups that we can come out of that structure. And what we tend to find is, this is quite a complicated picture, but I'll show you another example. What we tend to find is that, very similar to how brains function in complicated brains like we have, or even simplistic brains like in insects or worms, or simple organisms with smaller brains. This is kind of a similar process, in that neurons are linked together to become useful pathways. And the more that those pathways are used, the stronger they become, and the less they are used, they tend to die off. And it's kind of like a natural building of the useful pathways that are actually used in your brain. It's kind of similar to if you learn a language when you are very young and you don't use that language very much when you get older, you'll always retain some of that language, especially if you learnt it when your brain was forming. But you'll start to forget parts as you're not using the pathways in your brain that relate to that language. If you learn it as an adult when your brain's more developed, it's much harder to establish those pathways, so they sort of fall apart more quickly. So, for example, I have a high school level in Spanish, and I can't remember any Spanish now to save my life, which is terrible because I put a lot of effort into it. So what we find is that the useful pathways of what agents were doing naturally come out. And the really nice thing about Azure Digital Twins is that we have this graphical interface. This is the Digital ADT Explorer, the Azure Digital Twins Explorer, which is also available from Microsoft as part of a GitHub repository that you can download and use. And it helps us as the researchers or the people using these systems to visualize what we are actually seeing. So in this case, we can see a simple run where we've got 6 agents, which are in green, and I'll sort of zoom into those. Each agent then has different memories or events associated with those. And you can see that depending on which run we do, the agents actually use different memories in different ways. They all pretty much create those memories, and then the memories can contain specific events. And you can add and adapt your data structure to whatever you need. So if you identified that there's an additional piece of data that you needed, you can adapt that. But what we can then very quickly visually see, which is really useful, is those sort of pathways. And I don't think we could see those in other graphical data tools, but we wouldn't be able to see those in other, in like a standard database, for example. Even though we may have all the information we require, we can't access it in a nice and easy to understand and easy to visualize way, which is why I really love the Azure Digital Twins tool. I did want to spend a couple of seconds or a couple of minutes that I have left to just give you a little bit more information on some of the other work we do with Azure Digital Twins, which is sort of more for its intended use case, which might help you contextualize some of the work that we've been doing. So this is a smart building example where we have a Azure Digital Twin of a real physical space. So in the thinking machines example, we may have an Azure Digital Twin of the agents within a real physical robot, but we also may have a digital twin of agents that only exist in gaming scenarios, or they only exist digitally. Whereas Azure Digital Twins usually is defined, excuse me, as a digital representation of a physical space. So in this example, we have parking monitors, lockers, desk and meeting room sensors, so we can actually see what people are doing, what devices they're using, what chargers they're using, and then we have a digital representation of that. And then, as I sort of mentioned right at the beginning, we can do a whole layer of analytics and AI with that data, which is really interesting. So these are the sorts of scenarios that we mostly think and associate Azure Digital Twins with. But in my experience, it's just quite a flexible tool, and has lots of different uses. So, excuse me. So in this example, what are some use cases for a smart digital space that has a digital twin? Was lots of different things, to be honest. Space management, so how you're actually using a physical space, occupancy, how many people are there, how's that space being used, down to a sort of, if in an office scenario, it might be desk level, in a retail environment, it might be how people are walking through. We have environment management, so it might be, modeling and reacting to different temperatures in different areas, different electricity usages, elevator use, and lots of different things. If we're seeing every day at lunchtime, lots of people are using the elevators in a certain direction, to go down out to lunch and then coming back the other way, we can automatically send elevators using AI to actually anticipate the usage before it happens. Scenario planning, so Azure Digital Twins are great for simulating as well, whether that's with thinking machines, whether that's with smart digital spaces, allow you to run simulations on your infrastructure, as well as a lifecycle management, so how you actually update your IoT devices, and service management, so actually looking at where things are. So if you have a facilities manager come in to fix something, they actually have a 3D representation of the building, the twin, and they actually know where things are. So with that, I will wrap up and say thank you. We're going to move on to the panel discussion session, so I'm happy to answer any questions that you might have as part of that. But thanks so much for having me, and looking forward to talking with.
Thanks, Fergus, and that I have a ton of questions for you. So and I feel really bad, because if you would have told me about Rory, I would have added him to the speaker list, and we could have heard his British accent, right?
Well,
so
that's what I was going to say, is next time, hopefully he'll be able to do a little bit more than he currently can. Also, as a total side note, I have a brain sensor on my desk as part of my cool toys. So I'm hoping that I might be able to drive him around with my brain without talking at all. So that would be super cool.
Okay, so you have me at the edge of my seat, and we're definitely going to ask you back. Let's go ahead and jump into our table talk on industry trends. And for this discussion, I'd really like to invite Rachel Johnson. And Rachel has been with